Welcome to Physics 2 Second Lab. In this lab, we're continuing from Lab 1, where we looked at two strips of tape, one floating above the other, that were both charged. And the main goal of the lab is to compare the electric force calculated using the point charge model from Lab 1 to a line of rod charges model. For this lab, we're only using a computational model using WebV Python Glow script. And as a brief preview of the results, by the end of the lab, you'll see that the total charge calculated from the point charge model is different from the rod charge computational model, showing that splitting the tape into segments gives a more accurate estimate of the real charge distribution. The main physics ideas in the lab are Coulomb's law, which describes the electric force between two charges, and we're using it to calculate how the bottom tape pushes the top tape upward. We're also using Newton's second law that states that the force equals mass times acceleration. Here, we're using it since the top tape is in equilibrium, so the net force has to be zero. And we are also using superposition principle since multiple charges create the combined electric field on the charge tape. The system of this experiment is the top tape, the one floating, and the surroundings are both the bottom tape and the earth. As the initial conditions of this experiment, we have that the mass of each tape is 0.0002 kilograms. The gravity is 9.81 meters per second squared. Distance between the tape was 3 centimeters. The tape length is 20 centimeters. And the charge is what we're calculating next. So this is how we found Q, the charge in one single strip of tape. So first we calculate the gravitational force, and we know that the gravitational force is the mass times the gravity, and this is the downward force pulling the top tape downwards. Then we use Newton's second law. We know that the tape is floating, so the net force is zero, and that means that the electric force from the bottom tape must equal to the force of gravity. Then we modeled the bottom tape as a rod of charge because the tape is longer than it is wide, treating it as a line of charges, and this gives us a more accurate electric field. By Coulomb's law, we know that the electric force must equal that electric field of the rod times the charge of the tape. So we now just solve for Q, rearranging, and after plugging in values, that gives us that Q equals 2.613 times 10 to the negative 8. And this is the value that we're using for Q in the simulation. As a brief explanation of the code, we first create the tapes, a top tape and a bottom tape, and split each tape into, in this case, we're using 20 segments, and each segment acts like a little point charge. Then we calculate the electric field using nested loops. And inside of that nested loop, we calculate the field of each dq bottom of each of the segments using the E field function that we defined earlier that applies Coulomb's law. Then we determine the force acting on the top tape by the bottom tape by multiplying the charge of the top tape times the electric field generated by all the segments in the bottom tape. And at the end, we're just creating arrows to make the model more visible. As a comparison between the models, the point charge model from Lab 1 underestimates the force because it treats the top tape as a single charge. And the rod of charges model is more accurate because it accounts for the distribution of charges all along the tape. And even though both models follow Coulomb's law and Newton's second law, the rod charge model better predicts the floating behavior and the total line of charge. Now, for the possible sources of error, some things that could have affected our result, for example, include the measurement of the tape's length. The distance or mass might not be perfectly exact. The tape could also lose some charge from handling or from the air. In our simulation, we also assume that the charge is uniform across the tape and that both tapes have the same total charge, which might not be exactly true in reality. For the first discussion question, if we treated the tapes as 1 point each, then the calculated charge would be smaller. And that is because a point charge puts all the bottom tapes charge in the middle, but the top tape actually feels the field from the whole bottom tape, especially on the edges. So the point charge model misses that, so it underestimates the force. And for the second discussion question, the estimates differ because the point charge model oversimplifies and ignores how charge is spread out. The rod model adds up the field from each segment, giving it a stronger net field and a higher, more realistic charge, and it matches the floating behavior better and it's closer to what really happens. Here you can see the results. In the model, you can see arrows coming out of all along the bottom tape, showing the electric field at every point on the top tape. And that's way more detailed than the point charge model we used in Lab 1, where it's just one field from a single charge. And the simulation also shows the net forces, gravity acting down on the center of the mass of the top tape, and the electric force from the bottom tape acting up as we predicted. And so the magnitudes are almost the same, which is why the top tape floats. So in conclusion, overall, the rod charges model matched the floating behavior much better than the point charge model. Breaking the tape into segments gives a more accurate electric field and a better estimate of the total charge. Thank you.